Today's topic is filters. Filters were introduced by French mathematician Henri Paul Cartan in 1937 and subsequently used by mathematicians as an alternative to the similar notion of a net. We first define a filter. Let X be a non-empty set. A non-empty family F of subsets of X is said to be a filter on X if and only if the following axioms are satisfied. The first axiom is F doesn't belong to F. That is, no member of F is empty. The second axiom is if F belongs to F and F is contained in H, then H belongs to F. That is, F contains all supersets of its members. The third axiom is if F belongs to F and H belongs to F, then their intersection, that is F intersection H, also belongs to F. And that is, intersection of any two members of F is also in F. And this can be extended to any finite number of members of F. And we can say that intersection of finite number of members of F is also in F. And if these three conditions are satisfied, then we say that F is a filter on X. Now we have remarks. The first remark follows from axiom second that X belongs to F. From axiom second, we know that superset of any member of F is also in F. And since F contains subsets of X and X is superset of any subset of X, and so X belongs to F. The second remark follows from axioms 1 and 3 that if F belongs to F, then its complement doesn't belong to F. Why? From axiom third, we note that if F belongs to F and its complement is also in F, then their intersection, that is phi, belongs to F, which contradicts axiom 1. And so this is not possible. That is, if F belongs to F, then X complement, then its complement, that is F complement, doesn't belong to F. Now the third remark follows from axioms 1 and 3 that F has the finite intersection property. From third, we have noted that intersection of finite number of members is also in F. From axiom 1, phi doesn't belong to F. And so intersection of any finite subcollection of F is always non-empty. And if we consider empty subcollection of F, then we know that its intersection is equal to X and X always belongs to F. So we can say that F has the finite intersection property. Now we have some examples. Let X is a set containing elements A, B, and C. Then if we take F1, collection of subsets of X containing doubleton A, B, and X, then we observe that F1 is a filter on X. Here, first we know that this is a non-empty family of subsets of X. And we note that no member of F1 is empty. Then we also note that supersets of its members is also in F1. And third axiom is also satisfied. That is, intersection of its members is also in this collection. And so F1 is a filter on X. If we consider collection F2 and F3, then similarly we can check these are also filters on X. If we consider collection F4 containing singleton A, doubleton AB, doubleton AC, and set X, then we can check F4 is a filter on X. because this is a non-empty family of subsets of X, and no member of F4 is empty. And we also note that here, in particular, if we consider set A, singleton A, then its supersets are doubleton AB, doubleton AC, and X, which are in F4. And so we can check second axiom is also satisfied. And we can check intersection of any two members of F4 is also in F4. In particular, if we take sets members AB and AC doubletons, then their intersection is equal to singleton A, which is in F4. And so F4 is a filter on X. Similarly, we can check F5 and F6 are also filters on X. Now we come to F7, which contains set capital X. And we can check this collection satisfies all the axioms. And so F7 is also a filter on X. And if we consider a collection containing singleton A and X, then this collection is not a filter on X. Why? Because second axiom is not satisfied. Here, singleton A belongs to this collection, but its supersets AB and AC are not belonging to this collection, and so this is not a filter on X. Now, if we consider collection doubleton AB, doubleton AC, and X, then this is also this is not a filter on X, because here third axiom is not satisfied. Here AB and AC are belonging to this collection, but their intersection, that is singleton A, is not in this collection, and so this is not a filter on X. And if we consider collection singleton A, doubleton AB, and X, then here we note that second axiom is not satisfied. Here singleton A belongs to this collection, but its superset, that is doubleton AC, is not in this collection, and so this is not a filter on X. Now we have a definition for any non-empty set X. The filter containing the whole set X is called the indiscrete filter on X. That is, in the above example, we can say that F7 is the indiscrete filter on X. Now we shall consider some examples. Let X be a non-empty set and let X naught belongs to X. Then the family F containing F such that X naught belongs to F and F is a subset of X is a filter on X, as can be seen below. Means here F is a collection of all those subsets of X which contain X naught. So first we observe that F is a non-empty family because singleton X naught belongs to F, because singleton X naught is a subset of X and X naught always belongs to this set, and so F is a non-empty family of subsets of X. Now we have to check the axioms. Here, since each member of F contains X naught, so no member of F is empty. So first axiom is satisfied. If F belongs to F and F is contained in H, then since X naught belongs to F, so X naught also belongs to H, and so by definition of this collection, we can say that H belongs to F because X naught belongs to H, so H belongs to this collection. Now we check the third axiom, let F belongs to F and H belongs to F. By definition of f, x naught belongs to both f and h, and so x naught belongs to f intersection h, and since x naught belongs to f intersection h, so by definition of f, f intersection h belongs to f. So all the conditions, all the axioms are satisfied, hence f is a filter on x. This is called discrete filter on x. Now I am giving you a home assignment similar to the above example. Let x be a non-empty set and let f naught be a non-empty subset of x. Then show that the collection f containing all those subsets of x which contain f naught is a filter on x. Now we shall discuss an example. Let x be an infinite set and let f be the collection of all those subsets of x whose complements are finite. Then f is the filter on x. As we can see that this is a non-empty collection because complement of x is 5, which is a finite set, and so x always belongs to f. Now we check all the axioms. Now we check first axiom. By definition of f, for any subset f of x, f belongs to f if and only if its complement is finite. And since x is an infinite set, so f is also an infinite set, so that its complement will be finite. And so we can say that every member of f is an infinite set. Thus, phi doesn't belong to f. Now we check the second axiom, that f belongs to f and f is contained in h. Since f belongs to f, so by definition of f, complement of f is finite. And since f is contained in h, so complement of h is contained in complement of f. And since f complement of f is finite, so its subset complement of h is also finite. So by definition of f, h belongs to f. Now we check third axiom. Let f belongs to f and h belongs to f. Then by definition, complement of f and complement of h are finite. And so their union is also finite. But union of complement of f and complement of h is equal to complement of f intersection h. That means complement of f intersection h is finite, implies that f intersection h belongs to f. Hence, all the axioms are satisfied. We can say that f is a filter on x. This filter is called cofinite filter on x. Now we have a remark. If we define cofinite filter on the set n of natural numbers, then it is called Frechet filter. Let us discuss an example. Let x T be a topological space and n of x be the collection of all neighborhoods of x. Then n of x is a filter on x. As we can see, clearly this collection is non-empty because at least the set x is a neighborhood of x. So x always belongs to n of x. And we can say that this is a non-empty collection of subsets of x. Now we check first axiom. As each member of n of x contains x, so no member of n of x is empty, and we can say that phi doesn't belong to n of x. Now we check second axiom. Let f belongs to n of x and f is contained in h. Since f is a neighborhood of x, so h is also a neighborhood of x, and so h belongs to n of x. Let f belongs to n of x and h belongs to n of x, and since f and h both are neighborhoods of x, then we know that their intersection, that is f intersection, H is also a neighborhood of X, and so F intersection H belongs to N of X. So all the three axioms are satisfied. Hence we can say that N of X is a filter on X, and it is called neighborhood filter on X. Thank you.